Okay, everyone. Can everyone hear me? Would you say yes? Okay, good. So we continue our discussions on these applications of the ground resolution theorem, especially in the context of proving, or doing some theorem proving for first order logic. And also we're gonna study the limitations of this type of approach, which is the fundamental limitation, which is going to be an undecidability result. So what we did before, we studied about scolemizations and the ground resolution theorem. They together, I told you, they can lead to a semi-algorithm to check validity of a propositional logic formula. Often, we're gonna use a more generalized version of the theorem, which is written in the slide. So this is the two theorems that we studied last time. So in the typical situations, we were interested in proving, so we are having some closed formula F1 up to Fn. And then we want to check, let's say Fn minus 1. Hey, we want to check whether they entail Fn. Okay. So all of them are closed formula. I mean, this doesn't really matter, but often the applications, this is the situation that we have. So that's the problem that we want to solve automatically in our ideal situations. So then what should we do? And the thing that we are doing is we prove this using essentially proof by contradictions. I mean, if you remember, not in the mathematical logic sense, but what you learn about proof by contradiction in your math course before, what you need to do is you first negate the conclusion and derive the contradiction. So what does that mean is we negate the conclusion, conjoin it with all the things that so this is our goal. So how to prove this? We negate the conclusion. And conjoin it with all the assumptions we have. And from there, we derive the contradiction. So what this deriving contradiction means? Deriving contradiction means is essentially the same thing as showing conjunction of every assumption together with negated conclusion is unsatisfiable. Contradiction means that there are no way of making all of this is true, right? So contradiction is equivalent to showing unsatisfiable. So now we are in a situation where we have a multiple closed formula, and we are interested in checking whether this conjunction of closed formulas is going to be unsatisfiable or not. So that's the property that we want to check. And then for that purpose, these two theorems that's written in the slides are very useful. The theorems say, essentially they together provide a semi-algorithm how to answer this question. Just because it's a semi-algorithm, it works when it's unsatisfiable, but if it's satisfiable, so we can't really prove this, then this algorithm may go into an infinite loop. Actually, this algorithm, naive version of the algorithm always goes to the infinite. So how should we use these two theorems? The first theorem, and it's written as a mathematical theorem, but what it really suggests is the following methodology. We first change F1 up to Fn to the rectified pre-next formula. So, I just wrote it as an F1 up to Fn in the theorem, but we say we just change F1 up to Fn, well, negation of Fn, to the pre-next formula F1 prime, F2 prime, and so on. So for this guy, the converted rectified pre-next formula, I will just write it as a Fn prime, okay? So this one is equivalent to negation of Fn. So we just change the above one into the one below, and then the one below is going to be the rectified pre-next. And then the theorem tells us, okay, for the next step, so this is a step one. For the next step, the theorem tells us we just scholemize each of them separately, but make sure we are using different scholem functions or scholem constant. And this is the second step that we're going to do based on this theorem. So if we scholemize, we end up with G1 up to Gn. And then because the theorem say the conjunction of F1 up to F1 prime up to Fn prime is unsatisfiable precisely when, if and only if, this is conjunction of these scholemized formula is unsatisfiable. So to check the original formula is unsatisfiable, which really go all the way back to this entailment check that we are interested in, then all we need to do is just to check whether this scholemized formula G1 and Gn, they together, so conjunction of this guy is unsatisfiable. So that's what we have to check. Let's just call it end here. Now, the question becomes how we can check this scholemized, the unsatisfiability of this conjunction of scholemized formula. And then the next theorem, this tells us provide a methodology to do this. The methodology is that suppose we change this G1 and Gn into the conjunctive normal form. Okay, so maybe. So we change each of G1 up to Gn to conjunctive normal, which preserves the meaning. So you can just change it to the conjunctive normal form. Or you can do what you learned in, I think, one of the exercise, or one of the lectures, which preserve satisfiability. So you can change it to this into a formula where you have a bunch of universal quantification followed by maybe G star 1. Okay, so that's what we obtain from here. And then another formula together with Gn star in such a way that the above one is unset if and only if the below one is unset. And then we make sure this is all CNF. Okay, so in this part we can do it without really using the theorem, actually. Then after this part, then we're gonna use a ground resolution theorem. So ground resolution theorem say, okay, once the formulas are of this form, checking unsatisfiability of conjunction of these formulas is the same as checking, deriving contradiction using resolution theorem prover from the ground instances of G1 star up to Gn star. Because this G1 star is a CNF, you just conjoin all of them. They are, conjoin these matrices together. And then they think about all the possible the ground instances of this guy, which means that G1 star, Gn star, and then you replace, you replace all of them in one go or separately, it doesn't really matter. So T1 up to Tn, so these are the ground terms. Which replace all the free variable x1 up to x, call it xm. Okay, and we do it for all the ground terms here, T1. So these are all the ground terms. If you keep doing this, there are infinitely many CNF formulas, okay? But you conjoin all of them together conceptually and try to derive a contradiction using resolution theorem proving. When you apply the resolution theorem proving, treats all these predicate symbol applied to the ground term, like T1, T maybe I1 up to TIK as a predicate symbol, some predicate variable, maybe TJ. Okay, so if you treat all these applications of predicate symbol to the ground term as predicate symbols, and then apply the ground resolutions, then so you can come up with some algorithms that check the contradictions. That kind of check whether it's possible to derive the contradiction from this infinite set or not. And that process, if we put all these processes together, that will give a semi-algorithm to check the validity of the original formula. So that's a step. The first step is we convert it to the rectified Prenix form. We score-lemmize each of the formulas separately using different score-lem functions and score-lem constants. And then we also convert it to the CNF, convert the matrices of this score-lemmize formula into CNF. And we just put those CNF together and try to derive a ground resolution proof of the box. In other words, ground refutation proof from the ground instances of this G1 star to Gn star. So that gives us a semi-algorithm. And then now what I want you to do, then this first theorem justifies the first step. This ground resolution theorem justifies the second step. This ground resolution theorem is appeared here because this is a bit generalized version of this usual resolution theorem for multiple formulas. Okay, so that's the reminder of where we are. So now, here's the one example I want you to solve. So let me just show, okay, that's the slide which contains the strategy. So here's an example I want to prove, okay? So this example, because my colleague is from Oxford, he's using examples from Oxford. I don't know how many of you are familiar, have been to visited Oxford before. It's a very strange place. And then Oxford has something called the university and departments. And separately, there are something called Oxford colleges. And things are very much like a Harry Potter movie. So in Harry Potter, there are schools which correspond to the computer science department and so on. And in Harry Potter, there are houses. So then these Oxford colleges are like houses in Harry Potter movie. So in the example, Oriel is one of the name of the college, which is a quite old college. And then this example talk about students who are in Oriel, okay? The first statement to say everyone in Oriel is either lazy or drunk or is a rower, okay? So another very big thing in Oxford is because there is some small river or stream that people like to do rowing. And then this one say the Oriel, that's lazy, rower, or drunk. And then the second statement say all rowers are lazy. The third say there is some person in Oriel who is not drunk. And the last one say there is some person in Oriel who is lazy. Okay. And then what we are interested in is to prove ABC entails, ABC implies the last statement D. Okay, so that's what we want to prove. And we want to apply all the things that we learned so far to answer this question, so how to do this. So we're gonna translate this previous statement into the logic. So we will introduce one predicate symbol O of X. So the variable X in the first order logic will now range over individuals in this, some persons, okay? Intuitively, it will represent a person. So O of X means that some person X is in Oriel. And then we will have a L of X that talk about that person X is lazy, R of X that talk about the person X is a rower, D of X which talk about the person is drunk. Okay. So here's a translation of these four statements into the logic. So then here's the formula F1, F2, and F4. So actually for F4, this is a negated version of the statement. The first formula say for every person, if the person is in Oriel, then the person is either lazy, rower, or drunk. All the rowers are the lazy. And then there is a person who is in Oriel but not drunk. And this last part, not this F4 is a negated version of what we want to check. But if you just remove the negation, that said there is a person who is in Oreo and that's lazy. I mean, that person is lazy. So really, the question we asked was whether F1, F2, 3, conjunction of these three guys entails actually negation of F4. I mean, we just want to get rid of this negation here. So that's why I just put the negation. And it's true, I mean, whether this is true, that's what we want to check. Maybe just write it like this. But then I said the proof by contradiction, say, I mean, checking this is essentially the same thing as, I mean, actually also the meaning of this entailments. I mean, actually it's a semantic entailment. This guy implies this one is the same as putting the negation on the top and then checking whether this guy is unsatisfiable. So it's a proof by contradiction. Okay, so that's what we want to do. And then putting the two negations, this is the same as F4. So what we are interested in is to check whether F1, F2, and F3 and F4, whether this conjunction is unsatisfiable or not. Or actually we want to prove it's unsatisfiable. So now how to do this? And we want to use I mean, this what we learned so far. So here's an exercise I want you to do. I want you to apply what you learned so far, and then answer this question formally by producing the ground resolution proof from this formula. So I will give you 3 minutes to answer this question. Okay, so let me answer this. So then the first step that I told you is to translate everything into Prenex form. So let's just kind of change the order a little bit and then change it to, I mean, the first convert everything into the rectified Prenex form where the matrix is going to be the CNF formula. So then if we do the translation for F1, so which call it F1 prime, That's going to be for X. And we convert this implication by negation and disjunction. So then that's going to be in this formula, X or L of X, R of X, D of X. So this is a rectified Prenex formula with this matrix is a CNF, but actually the F1 prime is in also Scholen form, okay, because it only have a universal quantification. Now for F2 prime, it's going to be for X, negation of R of X, disjunction L of X. But F3, we don't need to do anything. It's X, O of X, and negation of D of X. F4, we have to push negation inside, we get for X, and then conjunction get converted into disjunction. So we have O of X or negation of L of X. Okay, so now we have to scholemize. So if you do scholemization here, then the scholemizations let us convert this existential quantification. Scholemization can be done with respect, using the fresh function symbols as well as fresh constants. So if you scholemize, this disappears, and then we're going to introduce new fresh symbol C. It's a constant symbol C. Okay. Then, so that's an outcome of scholemization. And then for the others, they are already in Scholen form. There's nothing to be done. Now for the next step, so this is a step 1. For the next step, now we're going to apply the ground resolutions. So which means that we're going to instantiate this F1 prime, the universal quantification in F1 prime, F2 prime, F4 prime in any way we like, such a way that from the obtained collection of clauses, we want to derive a contradiction using resolution theorem, resolution calculus. So how to do this? So we first instantiate the first one with the only constant that we know, which is a constant C. So if we instantiate this, we have negation of not Q, should be O. So negation of O, C, and R of C, R of C, and D of C. Now this is one clause that can be obtained from the instantiations of F1 prime. Then we also instantiate this F2 prime using constant C, but that will give us some R of C and R of C. Now we apply the resolution proof step. The resolution proof step, if you apply it here, is gonna cancel this constant, R of C from here to here. So then what we obtain there is going to be drawing negation of O of C, L of C, and D of C. And now we instantiate the last one, with the constant C, and that's gonna give us negation of O of C, L of C. And if we apply the resolution proof step, and this time resolution proof step will cancel this L of C. So what we obtain there is going to be negation of O of C or D of C. Now we're gonna use this back, this F3 prime. Here we have two clauses, and then we just use one clause, which is O of C. And then apply the resolution again, the resolution proof step again, then we obtain D of C because these two guys get canceled. Finally, we use the other clause in F3 prime, which is a negation of D of C. You apply the resolution step here, that's going to produce a box, because I mean, we get canceled, they get canceled, nothing left that correspond to box, which means false. So we derive the contradiction here. So then we formally, by using these two theorems and we using the proof calculus, the resolution calculus, we formally proved the implications that we care about in the beginning. So ground resolution. Okay, so that's what you can do. And so now let's move on to the next example. So that's example that I just showed you. Here's another example that I want you to try. So this is the formula that we want to check. We want to show it's valid. Okay, and then the formula is actually parenthesis goes like this. So it's for x exists y, this implication true. Exists y for x, this implication true. In general, if P and Q involve both x and y, this is not true. Okay, this is true because the left-hand side of the implication only talk about x, right-hand side of the implication only talk about y. So that's why it's true. So it's it's true because of very special conditional variable. But we want to prove that it is valid using all the technologies that we learned so far. Okay, so then the first thing we note is that checking the validity of this is equivalent to checking unsatisfiability of negation. F is valid if and only if we can't find any counterexamples of F. So that's what this unsatisfiability means. And now if you put a negation of F, it's a logically equivalent by putting negation and using De Morgan's law. It's logically equivalent to the one that's shown here. Again, the parenthesis is, we have a parenthesis like this here. Another parenthesis goes to here. Okay. And then now we split this formula into two parts. The first formula is about the first conjunct. Second formula is about the second conjunct. So, and then we want to check whether this is unset. And then we want to use all the things that we learned, this scolemizations and the ground resolution to prove this is unset. So here's an exercise I want you to do and prove the unsatisfiability of F1 and F2 using scolemization and ground resolution, or this ground resolution theorem. And then one important bit here is that if you just apply the scolemization, you end up with a structure. So you will end up with a structure which doesn't have any constant. Maybe if you do it in a certain way, you end up with some signature. Actually, you end up with signature which doesn't have any constant. You have two function symbol f and g. They are unary function symbols. And then we have two unary predicate p and q. They are coming from here. These are coming from scolemization. And this P and Q, they are already in the problem, so it's in formula F. But now in this case, because we don't have any constant, the Hilbert universe will be an empty set. But then you can't really apply this Hilbert theorem and so on. All those things works when there is at least one constant symbol. So what I'm explained in this hint is that actually, even in this situation, adding some artificial constant C, which doesn't appear anywhere, doesn't really change anything. So checking the unsatisfiability of negation of F on the scolemized version of negation of F under this signature is equivalent to checking the unsatisfiability with this extra constant symbol C. And so that's the fact. And if you are want to more challenge, you can try to argue or come up with some reason why it is okay to add this extra constant C. I mean, if that make you confused, just assume that adding constant C is okay. And then apply the things that you learned so far and prove this example is unsatisfiable. Okay, I'll give you another 3 minutes to solve this exercise. Okay, so let me show you how to do this. Okay. Make it a bit smaller. Okay, so the first thing I want you to notice is adding extra constant symbol doesn't really matter. That's because if any formula f, if A satisfies the formula, then if we extend A with some extra constant C, so this means we extend the signature, so this A is over the signature sigma. This means C, this is a bit informal notation for plus some extra constant symbol C. So if you put extra constant C and then bind it to any value in the underlying universe, that still is going to satisfy F. I think that one of the students asked me a question like this. So this is more like a relevance lemma for the extra constant or extra function symbol. Even for extra predicate, the same thing happens. And that lemma is also true. So this is relevance lemma for constant symbols and function symbols and the predicate symbols. So it's a relevance lemma for this, not for variable, but for other part. If this constant function predicate symbol do not really appear in F, it is okay to so this means formula F is understood as a formula in sigma. Now here we are understanding formula F in a different signature, sigma over C. But if the formula doesn't use any constant C, whether this constant exists or not doesn't really matter. Okay, so this type of lemma is true. So that's why checking F satisfiability of F over structures over the sigma structure is the same as, this is informal notation. It really means the same as f is satisfiable over this extra constant C structures. Maybe appropriate things to say is, these two guys are actually equivalent. They are say the same thing. Okay, so this is the technique that we're gonna use. So how to use this to solve this question. So here's how we do it. And we have a F1 and F2. So then formula F1, if we scolarize, we end up with F1 prime. The F1 prime, say for X. So I will change this negation as a disjunction. So then we have a P of X, negation of P of X, or Q of F of X. So this F was coming from scolarization. Okay. And then we also have F2 prime. Okay, so the F2 prime is I push the negation all the way back, then this existential quantification becomes universal. The second existential, the universal becomes existential. So then we have for all y. Now, if I scolarize the second existentially quantified x, so then I end up with P of g of y, or the q of y. Okay, so this is the formula that I have. Right. Okay, so now we're gonna, let me see. No, I was wrong. So because of the negation is pushed inside, this is just a naive translation of implication. I have to think about the extra negation outside. So that's equivalent to for y, have a P of G of y and negation of Q of y. Okay, so this is what we have. And from this F1 prime and F2 prime, we want to derive contradictions. Okay, we want to derive grounds, in a sense, refutation proof. How you do it? So we first, so then that means that for x and y, we can plug in any of the ground terms. For also there, because we only have a function symbol f, so we will introduce new constants. See here. Okay. So in this setting, so here's how the proof works. So we first instantiate the top things using g of y. So here's the plan. The plan is we instantiate this f1, this matrix of f1 prime, which is this part. And instantiate this part. And then we will get rid of all those, all those atomic formulas in that disjunction. So we're gonna want to get rid of this guy and get this guy by instantiating f2 prime appropriately. Okay, so that's our plan. So then how we should instantiate f1 prime, then here's a strategy. And so we're gonna instantiate f1 prime such a way that this guy is can be eliminated by the corresponding one here. Okay, so to do so, we instantiate this using P of G of C and Q of, because X is now replaced by G of C, we have F of G of C. Okay, so that's coming from F1 prime by ground substitution, or instantiation, substitution. Okay, and then, okay. And then now we instantiate f2 prime. the one of, and we replace y by constant c, and then take only first clause in this conjunction. So if we do so, then we end up with p of g of c. That's coming from f2 prime with this specific instantiation. Now we apply the resolution. Resolution said if we have the same thing that can be canceled, if we have a two clause, which means a disjunction of atomic formula, disjunction of literals, and then the one positive, one negative, they get canceled each other, so they get canceled. So then the remaining part is q of f of g of c. And then now we instantiate f2 again, f2 prime again. Now, when we do the instantiation, replace y by f of g of c. So this is again coming from f2, but with a different instantiation. Then we have q of f of g of c. And then we apply the resolutions, and they will cancel each other. And we obtain the contradiction. We will obtain a box here. So that's how you can derive the contradiction using ground resolution here. Okay, I mean, this is quite simple, but I thought it's good to know about, at least see some examples about how all this works. Okay, so here's resolution. And then now for all these theorem implies that the validity of first order logic is semi-decidable. And this algorithm is actually the algorithm that I told you was this semi-algorithm is a semi-algorithm that I told you a few times. So here's a reminder. The algorithms take a closed formula F, and then the goal of the algorithm is to check whether the formula is valid or not. But the way this algorithm behaves is that if the formula F is valid, then this algorithm will return and say the formula is valid. And then the output of the algorithm will always be correct. Okay, so if the formula is valid, then the algorithm will return the formula and say the formula is valid. Otherwise, the formula is not valid, the algorithm go into an infinite loop. And then the step of the algorithm is exactly what we discussed so far. You first apply this change f to put the negation first, because now instead of checking the validity, we check its negation is unsatisfiable. In other words, whether we can't find the counterexample from for f or not. So if we check a negation, if we can prove it's unsatisfiable, that means this formula f is valid. And then we apply this Prenex, to change this negation of f to the Scolen formula by first going through this changing formula into the Prenex rectified form, and then apply the Scolemization, and that will give us Scolen form formula G, with whose matrix, whose unquantified free part is a CNF. That is satisfiable with the original formula negation of F. And then we consider all those ground that the enumeration of Hilbert expansion of this formula G. And then we take a finite prefix and check this finite prefix has a resolution refutation. In other words, it has a proof of contradictions according to the resolution prover. And that can be done algorithmically. And we check this for every finite prefix. If some check succeed, we return and say f is valid. Otherwise, we go into the infinite loop. And that's the algorithm that I told you a few times. But existence of the algorithm implies the validity of first order logic is semi-decidable. Now yes, that's right. The resolution star is defined in one of the slides on the resolutions, but it's really try to derive all the consequences from the resolution proof rule. And that can be done, that can be done algorithmically. So you just do it, derive everything. If all the derived thing contains box, so then we say there's a desired contradiction, the original formula is valid. But they say the same thing as checking whether we can prove contradiction using resolution theorem prover for G1 up to Gn, which can be done algorithmically. So there's an algorithm to do it. because G1 and Gn are quantified free formula. Essentially, they are propositional logic formulas. Okay, so then the next question, natural question is, can we do better? So can we design an algorithm instead of a semi-algorithm? In other words, can we get rid of this infinite loop? It turns out the answer is no. And then to prove this answer, we're gonna look at so-called post-correspondence problem. And we will reduce this post-correspondence problem into the validity problem of first-order logic. And I don't know how many of you heard about in these reductions in the computability theory and complexity theory. And here but this is a kind of very common techniques that you can use to show some problem is either undecidable or NP-complete. And in this context, we are more interested in undecidability. So these techniques of reduction goes like this. To suppose I'm interested in showing some problem Q, but in this context, we are interested in whether this validity problem for first order logic is decidable or not. So this is what we are interested in, and we want to actually show it's not decidable. Then how to do this? Then to do so, we pick one undecidable problem. So this is a problem that's known to be undecidable. What do you mean by problem? Problem means that it has an instance of the problem, which is called I. And then what we have to do, solve this problem is for each instance, we have to say, because it's a decision problem, we have to say yes or no, according to some specification. And then undecidability means that there are no algorithms that take an instance and return yes and no correctly all the time. Okay, so that's what undecidability means. So we take undecidable problem and we reduce this undecidable problem for the validity problem. And how you do it? Essentially, what we have to do is to come up with a translator. So that translator take instance I of the original problem and produce some formula in first order logic. So that's a instance in this validity problem. So F is a mapping that take instance of the problem P to an instance in the validity question in first order logic. So this is a formula in first order logic. But we design F such a way that it satisfies two things. The first, if we should map I to yes, if and only if this F of I is valid. Or F of I should be mapped to yes according to this validity problem. So this translation preserves, the answer, okay? The F of I is valid if and only if the original one should be mapped to yes. Second, F should be computable. So essentially there should be an algorithm that take instance of the original problem P and produce a formula in the validity question. So if we satisfy these two, that implies we can't really have an algorithm for validity. That's because if we have an algorithm for the validity, we can design an algorithm for the original problem P by this composition. So for original problem P, we take I, and then we map it to the validity question by applying F. And then we apply the algorithm for the validity to answer this F of I is valid or not. That will give would give an algorithm for solving the original problem P, but that's not possible because the P is known to have no algorithm at all. Okay, so that's the idea of reduction. So to say it again, the important bit is that for reduction, we have to find this translation that preserve the validity and also it is computable. And assuming the original problem is unsatisfiable, existence of such an F shows that validity is also unsatisfiable. Because otherwise, no, not unsatisfiable, because original problem undecidable, this existence of such a mapping F shows that validity is also undecidable. And then, I mean, the polynomial time reduction in MP, the complexity theory has essentially the same flavor. There, instead of undecidability, we have a so-called NP-complete problem, and this F should be not just computable, but should have a polynomial time. And more complicated class like a P-space and so on, they also have a very, very similar flavor. Okay, so it's really proof by translating known hard problem into the problem that we care about. Okay, so that's a strategy that we're gonna use. Then the question now becomes which kind of undecidability problem we're gonna use in this context. And then the problem we're gonna use is something called post-correspondence problem. So this is invented by the person that you see on the screen, whose name is Emil Post. I mean, he was also one of the kind of founding fathers of logic and recursion theory and computability theory in the beginning of the 1900s. And what I heard that he made contributions in the many aspects of the computability theory. So he came up with something that is very close to the Turing machine. Later, he came up with another formalization of computability in terms of by means of term rewriting, which has a huge influence on the theory of programming languages. And some interesting stories that, after his PhD and his postdoc in Princeton for about a year, he was a high school teacher for quite a while before he became a professor in one of the universities in New York. And another story that I heard is that, he had some illness, so his doctor advised him not to work or not to do research more than 3 hours per day. So that's what he did, perhaps in his life. Okay. So what is the post-correspondence problem? So post-correspondence problem is one of the undecidable problem that Post came up with. And the problem is actually quite simple. Okay, the problem say that the instance of the problem is a set of tiles, and mathematically set of tiles, each tile is nothing but a pair of 0-1 sequence. Okay, so one instance of post-correspondence problem can be something like this. We have 3 tiles. The first tile is this pair, which is a sequence 1 together with sequence 0, 1, 0, 1. Second tile is 1, 0, and then 0, 0. So this is x2 and y2. This is x1 and y1. x1 is the top guy, y1 is this guy, x2 is this one, y2 is the one below. This is x3 and y3. So in this case, we are given 3 tiles. And then the question is whether we can find a sequence of tiles such a way that if we have put all these tiles according to the sequence, we'll have a 2 string, one coming from x part, the other coming from y part. And the question, this PCP question asks for whether we can find such a sequence such that top sequence and bottom sequence is the same. So this is what you see on the screen is one arrangement. The first one coming from the first tile, the second one coming from the third tile, the third, second tile, this one also the last tile. So we arrange tile 1, tile 3, tile 2, and tile 1. Okay. So that's the arrangement. But if you see if you concatenate the 0-1 sequence on the above the x part of these tiles, y part of these tiles, they will be the same. So it's a 1, 0, 1, 1, 1, 0, 0, 0, 1. So it's a 1, 0, 1, 1, 1, 0, 0, 1, 1. The one below is exactly the same, 1, 0, 1, 1, 1, 0, 0, 1, 1. If you compare them, it's exactly the same, right? 1, 1, 0, 0, 1, 1. So in some problem instance, which is a set of tiles, it is impossible to come up with a solution. Some problem instance, it is possible to come up with such a solution. So the decision version of PCP problem asks whether there exists a solution for a given set of tile or not. So that's the PCP problem. And it turns out this PCP problem is undecidable. Okay. So the PCP problem, well, here again, instance of PCP problem is a finite set of pairs, and each component of the each component of the pair is a sequence of 0 and 1. So these pairs, each of these pairs should be understood as a tile, and a solution is a sequence of indices of these tiles, such a way that if you take X component and concatenate them together, take Y component and concatenate them together, they are the same thing. And this is, in some sense, easy because the problem is quite simple. In other sense, it's hard because the possible set of sequence. So it's a sequence of indices. There are infinitely many of them. So it's not entirely obvious whether there is an algorithm that can come up with this sequence of indices or check whether existence of such a sequence of indices. And it turns out there's no algorithm at all. And this is known to be known undecidable problem. So decision version of this PCP is given the sequence of finite set P, we want to answer whether there is a solution of P or not. So this is either yes or no. And designing an algorithm that takes P and then returning yes when this is the case, no when this is not the case. That's the decision version of PCP problem. And it's known that this decision version PCP is undecidable. Okay. So now what I want you to do is to use this decision version of PCP problem to show that the validity of first order logic is undecidable. So here's the one exercise, one specific instance and one exercise I want you to do. So here's a particular instance of the PCP problem where we have three tiles, 1, 0, 1, 0, 1, this one and these three tiles. And then we plan to encode this problem into the validity problem in first order logic. And here are some schemes of the encoding. So to do this encoding, we're gonna use one constant symbol called E, two function symbols called F0 and F1. Okay, and then essentially the ground term in this setting will encode a sequence of 0 and 1. Okay, so this is one ground term obtained by applying the F0 to E first, F1 to the outcome, F1 again, F0, and then F1. This one, we're gonna write it as like this. So it's an abbreviation of this sequence of function application. So this is an abbreviation of this sequence of function application. And then this one is gonna be used to encode a sequence 1, 0, 1, 1, 0. Okay, so that's what we're gonna use. And then we will also have one more predicate. And that intuitively what that predicate should express is the predicates say X and Y are related precisely when the string represented by X and string represented Y can be built by a sequence of given tiles. Okay, it can be it is something that by just listing this sequence of tiles we can construct this. So for instance, we are expecting we have a P, this one is true, F1, 1, 0, F1, 0, 1, 0, 0. We expect this to be true. That's because, this sequence, what the sequence represented by this, which is 1, 1, 0, sequence represented by this ground term, which is 1, 0, 1, 0, 0, that can be constructed by putting these two tiles together. Okay, so what I meant is that we given this problem, we want to encode the problem into the validity question in first order logic, and then to do so, we're gonna use constant symbol E and the unary function symbol F0 and F1 and one binary predicate P, and then they will be designed according to the explanation that I have just given here. So now here's two exercises I want you to do. The first exercise is design a formula that express this highlighted red part of the slide. Okay, that formula, that first order logic formula, that for this specific instance of this PCP problem, that first order logic formula say P of xy is true if and only if the pair of strings can be built by a sequence of these three tiles. So that's one question number one. Question number two is that once you have this formula, and then you can, once you have this formula, you can actually encode that this decision problem of PCP and also try to do this. That's the second question. So I will give you 3 minutes to solve this question. So okay, so let me tell you how you can do it. For the for the first exercise, we want to write first order logic formula such a way that that formula really express the highlighted red part. Now the highlighted red part say, here's a way to encode this. You can think of this as a kind of recursively defining what this P should say. If you think about this recursive definition, Px, X and Y can be generated by a sequence of given tiles. Then if we do check the property inductively, there are base case where we are using only one tiles. There are inductive case where we have X and Y that's related by P, extend this P related XY with one extra tile. So that's how we do this. So we said, in this case, the sequence, the terms representing this sequence in this, and then 101 is related. That's because of the, that's because of this first tile that's given. And then we say the same thing for the second tile. F10E and F00E. And also say the same thing for the third tile. So this covers the base case. Okay? So this covers the case where the length of the sequence of tile is 1. And now we are thinking about the inductive case. And then so that's a formula 1. Formula 2 is covering the inductive case. Then inductive case say for xy, if xy are related by p, which means that there is a way to generate sequence x and sequence y using the x and y using a sequence of tiles. So then it is also possible to generate p of f1 x f101 y. That's because we can put this first tile to the beginning of the sequence. Also, we can generate f10x and f00x, no, 00y. That's because we can put this second tile to the beginning of the sequence. The same thing for the third. f11y. Okay, so that's, and these two, f1 and f2 together, captures this highlighted statement. Now, once these two captures the highlighted statement, then the question that we are, so they really say P express what we want, which means X and Y are the sequences, represent the sequences that can be generated by a sequence of tiles. So then we can write down the F3, statement F3, that express what we are looking for, which is we are looking for a solution of the PCP problem, which say that there exists a sequence of 0 and 1, which can be generated by a sequence of tiles. When a sequence of 0 and 1, which can be produced by a sequence of tiles where it's the same as upper part and lower part of the tile. So this is really saying there is a solution of this PCP problem. Okay. So if you put all of these together, okay, right? So this means that now what we are looking for is we want to say if P correctly encodes our intention, then we want to check whether there is a solution F3 or not. So the problem that we are really interested in, the proper encoding is that F1 conjoined with F2 implies F3. So if P properly encodes the problem, then there has to be a solution of this PCP problem. So this, I mean, that's really say the same thing as the original PCP with 3 tiles that's given as a solution. So this is valid if and only if that's the case. Now, as I said, I mean, so this is the encoding of this specific problem. And as I said, if we have this type of encoding, I mean, if you think about F1 and F2, how we constructed F1 and F2 and F3, they're all constructed algorithmically. And so this condition, I mean, have to check this, but this condition is actually turned out to be true. So this translation gives, I mean, at least this, if we can generate this translation for arbitrary PCP instances that give undecidability of the validity problem. So let me just go next. So that's the encoding that I just told you. I mean, there's a actually this F is not F1, F2, and F3. I mean, this has to be, I think there's just some typo. So really the formula we care about, we want to check this is valid or not. So the formula we care about is, these implications. That's what we care about. And then the checking this validity, is really, we convert it to unsatisfiability and so on. Okay. So more generally, here's the encoding of the problem. So if we are given this general PCP instance, which is a pair of tiles, set of, so it's a set of tiles. Each tile is a pair of 0, 1 string. So then we can create something like F1 and F2 and F3 from this P. And then the constructed part is essentially the same thing. F1 is the base, F1 and F2, they together say that P say the right thing, which is P relate to X and Y if X, Y can be generated by a sequence of tiles. So F1 and F2 together, they describe the predicate symbol P. There are two P's, so it's a bit confusing, but predicate symbol P says what we want. And then the F3, so the F1 is about the base case, F2 is about the inductive case. F3 say PCP has a solution. So you can see that once you have this type of encoding, then you can kind of see the following the proposition that appears here, which is P has a solution if and only if the F1 and F2 implies F3. This formula is valid. If conjoined F1 and F2 say if predicate symbol P say what we want, then our PCP should have a solution. So that's the, what this implication is saying. And then it turns out that this P has a solution precisely when this implication formula is valid. And you can actually prove this theorem. So you just have 2 minutes. So here's what I'm going to do. I'm going to just ask you to think about how to prove this theorem. Then next Monday, I will prove this theorem and then finish off this set of slides and then move on to the next topic. Okay. So, if you want to do it in your own time, you can just leave now and I'll stay here about 5 more minutes. And that's it for today. If you want to stay and solve this question, you can do it. If you want to leave, then you can leave. Anyhow, I'm going to be here 5 more minutes.